This is a bit of an introduction to our speaker. This lecture is joint between RASC and CASCA, Canadian Astronomical Society, and it was established as the Plaskett Medal in recognition of the pivotal role played by John Stanley Plaskett from 1865 to 1941 in the establishment of astrophysical research in Canada. Plaskett helped to confirm the rotation rate of the Milky Way galaxy. He was an active member of the Ottawa Centre between 1907 and 1918 and acted as an associate editor of the journal for 28 years. Wow. That seems like it runs in the family, doesn't it? The award, which consists of a gold medal, is a significant chunk of gold, and was first presented in May 1988, is made annually to the PhD graduate from a Canadian university who is judged to have submitted the most outstanding doctoral thesis in astronomy or astrophysics in the preceding 2 calendar years. The recipient is invited to address one or the other of the sponsoring societies at his or her choice at their annual meetings. And in this case, Dr. Anne Archibald of the Netherlands has chosen to join us here today with her talk. We are honored to have her with us. I'm going to ask you to give us your own bio. Where did you go to school?
Thank you. So I'm not actually from the Netherlands. Born in Montreal, I'm a Canadian. My family's here. So I went to school my undergrad was at University of Waterloo. I did my master's at McGill and my PhD at McGill, and I'm now doing research in the Netherlands. I guess, shall I just start, or? All right. So I should apologize up front for the title of my talk. This is my PhD work, and like all PhDs, it's a very detailed study of something very, very specific. And I would also like to apologize for the name of my object. It would be lovely if we could name all our objects, Joe or Sam or Betsy's star or something, but unfortunately there are so many objects these days that we have to have a naming scheme. It saves disputes too. Who discovers it first gets to name it. It is complicated. So unfortunately, many of our objects are named based on where they are in the sky. So this is PSR, because it's a pulsar, J for which coordinate system we're using, and 1023, 10 hours, 23 minutes, plus 0 degrees, 38 minutes. So that's just where it is in the sky, right on the equator. Also right in the plane of the ecliptic, which it turns out matters. Anyway, so this is an object that I found that my PhD research was studying. And like I say, it's a very specific object. But it turns out that this object, in fact, there's now a class of objects like it. And they are great laboratories for helping to understand accretion. So a quick overview of the talk. So I know that you are all interested amateur astronomers, but that means you know a lot more about finding your way around the sky than I do, but some of the things I study are a little bit unfamiliar to you, perhaps, because they tend to be visible in radio or X-rays, but not so visible in optical. So I'll give a quick overview of what pulsars are and why they're interesting. I'll talk a little bit about accretion, again, what it is and why it's interesting. And then I'll talk about the object I'm studying, which is actually a pulsar that sometimes accretes. It goes back and forth between accreting and being a pulsar. And then I'll talk a bit about finding more links between these two classes of object and what that can tell us and how we can do it. And here I think I'm going to be asking for help because one of the key ways we can find it is optical monitoring. And these are objects that are accessible to amateur astronomers. And in fact, some of the key discoveries have been made by amateur astronomers. So I'm going to be asking for help at the end. But, okay, and yeah, if you have any questions, or if you can't hear me or something, raise your hand and I'll try and do something about that. All right. So, supernovae, I think you are familiar with. Many of you have certainly seen supernovas. Some of you, I think, have discovered supernova. Anyone who has seen a supernova? Almost everybody. Well, then you probably all know that they happen, that sufficiently massive stars explode when they reach the ends of their lives. And what's left afterward? Well, there are three possibilities. Some supernovae, and I find this puzzling, actually blow up and leave almost nothing behind, just wisps of gas, diffuse, exploding out into the space. Some are really big and leave black holes behind. But some of them leave neutron stars behind. And in fact, this is 1987A, which you probably all know about, and it is supposed to have left a neutron star behind, but we can't find it. We should be able to see it, we think, but it's still missing, so we're just looking. But a neutron star is this stellar remnant, this cinder, this incredibly dense object. It's 1.4 times the solar mass, plus or minus a bit, 1.4 times the mass of the sun, but it's crammed into a 10-kilometer radius. These are incredibly dense. They may be a little like preposterously large atomic nuclei. They're just totally alien to us, actually. Nothing like them exists on Earth. But lots of things like them exist in space, because actually there's a lot of supernovae. I think there's, what is it, 3 per century in the Milky Way is supposed to happen. We're kind of behind. We're due for one soon. There are lots of supernovae, and there are lots of neutron stars. And they just sit around doing nothing for a long time. But they don't always do just nothing. So a pulsar, when you compress all this matter down to a tiny sphere, well, actually, you compress the magnetic field as well. And the strength of a magnetic field is a density. And so when you take a star's magnetic field and you cram it down into a little tiny sphere, you get these really strong magnetic fields, billions to trillions of times as strong as the Earth's magnetic field. And these magnetic fields, just like the Earth has an aurora over the North Pole, neutron stars have an aurora, which is actually these towering sparks extending up over the magnetic poles. And these towering, enormous sparks produce these beams of radio waves. And since the star is spinning, and since the magnetic pole is not always lined up with the rotating one, you get these beams that sweep across the sky, like a lighthouse. And if the beam sweeps across the Earth, then we see a flash every time it goes around. And this is just a little tiny, very incredibly smooth ball spinning in empty space. So they spin very, very regularly. So we get a pulse very, very regularly. And we can see those pulses with radio telescopes. There we go. We can see those pulses with radio telescopes. And so, for example, the Crab pulsar, we see a pulse 30.2 times a second, and we can measure the arrival times very exactly. And it's actually getting slower, very, very slightly slower. The period is 33 milliseconds. That period gets longer by 38 nanoseconds every day. And the Crab is actually one of the most vigorously spinning down neutron stars we know. So we have these precision measurements of these objects. They're great if you want to measure things exactly. And they have this tremendous energy bound up in their rotation. If you know roughly how big it is, you know roughly how massive it is, so you know, like a flywheel, how much energy is bound up in its spin. And you know how much it's slowing down, so you know how much energy it's losing. And if you work out how much energy the Crab pulsar is losing to spin down, it turns out that it's losing about the same energy it takes to power the entire Crab nebula. So M1 is completely powered by the slowing down of this neutron star. This little tiny 10-kilometer object spinning in space is driving this entire spectacular nebula that many of you have probably seen with your own instruments. And so these pulsars are spectacular objects that we can see from a long way away. And in fact, and it's the pulses that make them most distinctive. Normally you see them in radio, but they are also, a few of them, including the Crab, are visible in the optical. In fact, there's a story that Jocelyn Bell, discoverer of the first pulsar, Jocelyn Bell likes to tell this story, that before anyone had seen the first pulsar, before anyone had discovered them, there was a public star night at one of the big observatories. I'm afraid I've forgotten which one. but one that had a fairly big telescope with an eyepiece still on it. And so public star night, hosted by some senior astronomer, they're looking through the telescope, and they're looking at the Crab Nebula. They're looking at the point source in the middle, because they knew there was a point source there. It was classified as a very peculiar star, 'cause it's a funny color for a star. Not least because it's a weird neutron star. So people are looking at it, and one of the public, this young lady, well, adult, but younger than the senior astronomer guy, says, "Hey, is it flickering?" Public astronomer guy says, "No, don't be silly. That's just the atmosphere. It's twinkling." And she says, "No, I'm a pilot. I know twinkling. Looks like it's flickering." She says, "Don't be silly. Don't be silly." And indeed, the Crab pulsar optically does pulse, but it pulses at 30.2 times per second. And that's a flashing frequency that most people can't see flashes. Some people can. So she probably really did see it. Didn't believe her. Didn't find it. It took a grad student looking at Miles' chart recorder paper several years later to actually find the first pulsar. So, the two things that you can sort of reliably measure from a pulsar, the two easiest things to measure from a pulsar are how fast is it spinning, because you see the pulses. Often all you see is the pulses. The Crab is spectacular and close and bright, but many pulsars, all you see is the pulses, and then you see how much they're slowing down. So if you just plot how fast they're spinning against how fast they're spinning down, don't worry about the numbers there, but you just sort of plot them. And the thing that you should see from this graph is there's two big clumps. These ones are the normal pulsars. The Crab is up here, I believe. These are just normal pulsars. They spin sort of about once a second, and they're spinning down. And we know how fast they're spinning down, so they'll keep doing it for a few million years. And then they get too slow, and we don't see them anymore. But you should look at this and see, wait a minute, what are all these ones here? They're spinning way, way faster, hundreds of times per second. This is kitchen blender speed. This 10-kilometer radius sphere is spinning at as fast as a kitchen blender. How do you get all these guys, if they start maybe 30 times a second and slow down, how do you get up to hundreds of times per second? And it's been a puzzle. Well, the first one was found, and now we've found lots of them. They're much faster. They seem to be very old. They're spinning down extremely gently. They can keep doing this for billions of years. And they are also mostly in binaries. They're mostly not just isolated. They're mostly orbiting another star, orbited by another star. And that's, it turns out, not a coincidence, because as far as we can tell, the way you get these guys, these millisecond pulsars, is that you take a young pulsar, it spins down, it disappears a few million years. Eventually, maybe a billion years later, the companion it's around gets so close, material starts falling on the pulsar. This is accretion, which I'm going to talk about a bit. But the material swirls inward, and that swirling inward, like, you imagine water going down a bathtub. If you have a ping pong ball floating there, the ping pong ball will start spinning. The swirling material spins the neutron star up to these incredible speeds. So this was a process we kind of thought happened, but we hadn't quite seen it happening. And in some sense, now we have. But so accretion is a process that happens not just to neutron stars. Actually, if you've got a big blob of gas, and you want to turn it into a star or a galaxy or something compact, it has to fall inward. And that falling inward is accretion. And accretion, it's how planets form, it's how stars form, it's how solar systems form. We see black holes at the center of galaxies are these spectacular quasars. This happens through accretion. It happens all over the galaxy. And this is how neutron stars get up to these really high spin periods. But it turns out that accretion is complicated. You think just gravity, it's just falling. How complicated can falling be? Well, okay, it's falling, but it's not all falling inward, some of it's falling sideways, so it swirls a bit. But okay, swirling we can swirling is vague, but we can at least try and understand that. But it turns out that it's a lot more complicated than that even. But it shouldn't be hard, right? Because accretion is bright. If you drop some material into a black hole and it swirls on the way down, you can actually, the amount of energy you get out is like half of mc squared. That, nuclear fission releases maybe less than 1% of mc squared. So if you set off an atomic bomb, a tiny, tiny, less than 1% of the mass gets turned into energy, and it's spectacular. Set off a fusion bomb, it's maybe less than 10%. It's still spectacular. More than half of the energy that you can possibly get out of a hunk of matter comes out when it falls into a black hole. Neutron stars are slightly wimpier, it's only 15%. It's still more efficient at getting energy out than nuclear fusion. Nuclear fusion is pretty spectacular. So this is something that we can see. We can actually see it from across the known universe. This is a quasar, a nice X-ray picture of a quasar. These things are way, way out across the galaxy, across the universe. And we can see them. They're so bright we can see them. So accretion, we can see lots of things accreting. It should be easy, right? Except, turns out not. One problem is that, yeah, the big spectacular ones we can kind of try and get our hands on. But actually some of them are, and we don't know why, fainter than they ought to be. There is a supermassive black hole at the middle of our galaxy, Sagittarius A star. You can see it in radio. There's so much dust you can't see it in optical, sadly. But it's faint, in spite of being something like 1 million times the mass of our sun, potentially being one of these guys that pours out, megaparsecs of jet flying out of the intergalactic medium. Instead of being like that, it's less bright than our sun. We don't really know why. Even if you look at how much gas there is, it's not in a very dense environment. Even if you look at how much gas there is, the gas is falling in without actually releasing as much energy as it could. We don't really understand accretion at these low levels yet. In fact, there's a poster about this, or there was yesterday, a poster about this. The weak accretion is actually really puzzling. And accretion is really hard because you want to understand accretion. Well, accretion, what matters is matter. You've got this plasma that's flowing inward. It has to interact with a magnetic field, which always complicates things. And it also has to interact with strong gravity. And the interaction of all three of these phenomena is really hard to understand. And worse, you can't do it in a lab. We can't make, often the plasma densities are stuff we don't, densities and temperatures are not something we can do in a lab. The magnetic fields are often very difficult to get in a lab. And we don't know actually what they look like. We just know they're there. And gravity is very difficult to work with in a lab. I mean, you want to measure this, you want to see something swirling into a central object, you can't do that in a lab because gravity you always have this Earth's gravity pulling you downward. And it's hard to build objects that have interesting amounts of gravity. So this is really hard to get at in a terrestrial laboratory. So we really need objects in space that can serve as laboratories. And unfortunately, of course, we have these lovely, spectacular guys on the far side of the universe, but often all we can see is that they're accreting. It's hard to find out much about what's going on in them. So we need some other way of finding out about objects that are accreting. And we now have at least one kind of object where we can do that. Because this object that I found, PSR J1023+0038, again, sorry for the name, I'm going to call it 1023, spends some of its time as a pulsar, where we can use the nice, precise pulse arrival times to measure it, various other ways we can measure it. We can study it in detail as a radio pulsar, and then when it starts accreting, all the stuff we figured out here is still true. So we have a very detailed picture of what this looks like. It's like being able to turn off accretion, measure your system exactly, and then turn accretion back on, which is you would just do in a laboratory, but in space, often hard to arrange. But here, we can pull it off. So, how did we find it in the first place? Well, the way the first pulsar was found, Jocelyn Bell found it by looking, they were looking at for something else entirely. She found these, she called it scruff, these just weird bumps in their signal. And she was looking at miles of chart recorder paper, literal miles. Her office was strewn with this stuff. And she had seen enough, they didn't have cell phones in 1967, but they had plenty of radio transmitters. And they all show up on a radio telescope, believe me. And so she had seen lots of that. But that looked a little different. She looked with her own eyes at enough miles of this stuff to know what interference looked like and to know that the scruff looked different. She noticed also that the scruff turned up 4 minutes earlier each day. And that, as you know, is a sign that it's in the sky coming from the stars and not from the sun or not from our watches. So she spent some time and effort persuading her PhD supervisor to let her run the chart recorder faster the next time one of these guys came over. And sure enough, she got pulse, 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 pulse. So these radio pulses are still the easiest and best way to recognize a pulsar. They're very periodic, very regular. So how do you find pulsars? Well, the easy way, the way they found the Crab pulsar once they'd found the first one, was they thought, hey, Crab Nebula, supernova, huge nebula, bright, funny-looking star thing in the middle of it. I wonder if this is a pulsar. So they pointed a radio telescope at it, and they put it on their chart recorder, and sure enough, 30 times a second, nice radio pulses. Easy, right? They knew where to look. And we still find some by knowing where to look. But often we don't. Often all you see from a pulsar, or the first thing you see from a pulsar, is the radio. So if you want to find one, you just have to look and look and look. You search as much of the sky as you can. And you search with the biggest radio telescope you can. So this is the Green Bank Telescope in West Virginia. It's a radio telescope, which means the dish doesn't need to be a perfect mirror. It's pretty good, but it doesn't need to be good to the nanometer level. So you can build it big. This dish is 100 meters across. You could play a slightly lopsided game of football on it. Don't go too far into the end zone. But this is an enormous telescope. And it was a huge job to build, and people are really competitive for time on it. And if you want to search the entire sky, you have to look for a long time. So we cheated. In 2007, the telescope was being repaired. The azimuth track that let it turn east-west had worn out, needed to be replaced. So they couldn't move it. They couldn't track sources across the sky. In fact, all day they're running arc welders. But they shut off the arc welders. Arc welders are not good for radio reception, if this wasn't clear. Come evening, they would shut off the arc welders. We would pick an elevation for that day, and we would let the sky roll past. We'd record data from arc welders off to arc welders on in the morning. Now, we recorded a huge amount of data, but this gave us, we had almost 2 solid months of this. And so this gave us 120 terabytes of data, which is not totally spectacular now, but back in 2007, that was a lot of data. And then, so we just went through that data looking for periodic signals. And, you know, there are good algorithms, fast Fourier transforms, what have you, for looking for periodic signals in data. The problem is there are lots of periodic radio signals. If you turn on your car, the spark plugs fire periodically. If your cell phone goes off, the tower sends off periodic signals. There's lots of non-pulsars. And so we would get, from our search program, we'd get outputs of thousands upon thousands of periodic signals. And we have to go through them looking for actual pulsars. And I had gone through kind of a lot of thousands of signals. And I came across this. This is one of our output plots. And I thought, oh, wait a minute, this one looks promising. Because, you know, you've got a nice periodic signal. You've got it's present sort of throughout the observation. It's present across the whole bandwidth. This looks really promising. So I took this plot into my supervisor's office, and I said, do you think this looks real? And she said, there's your thesis. And as in so many things, she was right. This was a really interesting pulsar. This is a really interesting pulsar. It's not actually pulsing right now, but it's really interesting. And the reasons it's interesting, well, the reason we knew it was interesting right away was that it had a history. It wasn't a completely new object. It had been observed optically. The Sloan Digital Sky Survey had covered this piece of sky. And so had the first radio continuum survey. It had attracted attention. And in fact, so the Sloan people got an image of it. It was G-colored. And then somebody went back to look at a spectrum, and the spectrum was totally different from the colors. It had actually changed state. In 2001, it had actually lit up, and it was accreting. Whereas when the Sloan came by the first time in 99, it was a pulsar. So this attracted people's attention, but not a lot of attention. Sloan produced bazillions of interesting things. So nobody quite realized this was interesting. There were just a handful of observations before it went back to being apparently just a star. And so it was initially classified as a white dwarf that had some kind of accretion episode. One of these cataclysmic variables that AAVSO likes to look at. So it was sort of thought as maybe interesting, but nobody really knew that it was worth looking at. But once we had found a pulsar there, we had found something that had never been seen before. We had a pulsar that had spent some time as an accreting object. We had something that was going back and forth between this nice, clean pulsar state and this spectacular accreting state. And that we knew was going to be interesting. So we thought we should observe this with everything we could get our hands on, especially since if it had done it once in 2001, at any moment it could light up and do it again. So we decided to observe it with everything we could get our hands on. Well, optical telescopes are great, but to really understand something like this, it takes more instruments, because different instruments reveal different aspects of the system. So the optical telescopes can see the companion. Companion is actually, I'll talk a little more about the companion. Optical telescopes can see what's going on with the companion. The companion is a fairly normal-looking star. Well, it's not even spherical. It's kind of pear-shaped. But apart from that, it's reasonably normal-looking. And the optical telescope can see that and measure interesting things about it. But the pulsar itself shows up in radio waves. So use radio telescopes to observe the pulsar. It turns out that the pulsar is energetic enough that gamma rays are emitted. You can observe it with the Fermi Space Telescope and see the gamma rays from it. And the pulsar, like the Crab Nebula, puts out this wind of particles. And then when this wind of particles crashes into the companion, you get a shock. And that shock emits in the X-rays. So to understand the system, you want to combine information from the gamma rays, the radio, the optical, and the X-rays. And anything else you could get your hands on. We tried gravitational waves, but they didn't work. So we studied it with everything we could. And by combining them, we found out a lot of cool things. So for example, in the optical, the companion is sort of a G-colored star, 17th magnitude. And 17th magnitude is accessible to a modest telescope with a bit of patience. I'm not good with telescopes hands-on myself, but amateurs can observe this, have observed this. I'll talk more about that later. And even when it's just being a pulsar, even when there's no accretion, nothing changing in the system, you actually see, as it goes around its orbit, modulation. It gets brighter and fainter by about 0.4 magnitudes. And there are two things happening. One is the star is kind of pear-shaped, sort of viewing the pear end on, it's less bright than when it's sideways. But the other thing that's happening is that the side facing the pulsar is hotter. The pulsar is blasting it with antiparticles. That side gets hot. The other side is cooler. It's only about 400 degrees, so the color and brightness differences are minor, but you can see this companion going round and round. And you can kind of try and estimate what's going on from how much heating it has. So the optical gives you a lot of information, even just with photometry. You can also take radial velocity, and John Thurston did a lovely job of measuring the radial velocity. So that gives you sort of an estimate of the orbit, an estimate of the orbital size. And the pulsar gives you the other half. So combining the two, you get what's called a double-line binary. You know a great deal about the system. You know the ratio of the masses of the object is really valuable. So the optical was essential to what we were doing. And this was done with a fairly modest telescope. I think it's the MDM observatory. And you don't need a giant telescope to do at least this much. Although we did use some giant telescopes to try and really nail down exactly what's going on. But one of the other things we did, and I love this because this is absolutely classic astronomy, we measured the distance to the star. And this is the parallax method. You want to measure the distance to a star? Well, you observe the star against the background of stars from one side of the Earth's orbit and from the other side of the Earth's orbit, and it appears to move. You get this squiggle motion where it actually seems to move from side to side because you're seeing it from the other ends of the Earth's orbit, because it's not as far away as the distant galaxies. And measuring how much this squiggle is tells you how far away it is. And incidentally, the reason it's going this way, this is the motion. It's actually zipping through the sky as well at about 100 kilometers per second. And of course, we measure that. It's less interesting than the distance, but we're able to measure this. Now, this object is pretty far away. It's about 1,400 parsecs away, 4,000 light years, if you will. And that means that the amount of this motion, the size of the squiggle, is less than a milliarc second. It's tiny. Fortunately, this thing's a pulsar. So we use very long baseline interferometry to get these precision measurements. We use these radio telescopes, which are distributed all over North America, from the Virgin Islands up to Hawaii. And through very clever, very careful calibration, you can combine the phases of the telescopes and get the same resolution as if your telescope was the size of the Earth, more or less. This gives you these very precise measurements of the position. And Adam Deller led this project. We managed to actually get a distance measurement to the source. And this is great, because then you know if you see a brightness, you know exactly how much power is coming out of the stars. It's really valuable to have this distance. And it was possible because the thing was being a pulsar. Nice, bright radio source, tiny spot, as simple as we could get. And by combining all these observations, we were able to completely understand the geometry of the system. This is a diagram to scale. This is millions of kilometers. The whole thing more or less fits. The sun is about this big. The body of the sun is about this big. So the entire orbit of the system fits in the body of the sun. The companion fills about, occupies about it's about a companion width away from the pulsar. This is a really, really tight binary. It orbits in about 5 hours. But we know, for example, that we're viewing it from about a 45-degree angle, so it doesn't eclipse in the usual sense. The companion never gets between us and the pulsar. But we have this detailed picture of the system. And we have these precision measurements of things that don't change. We have the orbital period. I have more decimal places, but just to show what I mean by precision, the pulsar spin period we know to, how many is that? 19 decimal places or something? We are able to measure this to ridiculous precision. Nobody actually cares whether this is a 7 or a 5, but, well, I do, because I need to be able to predict the rotation. And if I slip a turn, I get very confused. But we have these precision measurements of the system. And this is really valuable when it comes time to understand what's going on the accretion side. So, also interesting, we know the magnetic field. We measure the magnetic field of the pulsar. And this is kind of weak for a pulsar, but strong by any terrestrial standard. This is about 100 million times the magnetic field of the Earth. And the point is that we know it. We don't have to guess what it might be. We know it. We measured it. And again, the pulsar is spinning down like the crab is, and the luminosity coming off is 13 times the luminosity of the sun. So we have all these measurements of the system that we were able to get while it was being a radio pulsar. And that was essentially the core of my thesis. Here's a complete description of this system as a radio pulsar. And around the time that I submitted, I got an email. I was thinking, oh, okay, it's time to work on something different. I get an email from my supervisor saying, hey, we haven't seen it in radio for a while. Do you think something might have happened? And sure enough, yes, it had started accreting. So the first thing we noticed was it disappeared as a pulsar. Unfortunately, it disappeared in June, and some of you may have already figured this out, but right at the plane of the ecliptic, June, 10 hours, means you can't look at it in the optical. Means you can't look at it with an X-ray telescope that doesn't like to look at the sun. It meant we kind of had nothing to work with for a couple months. So we knew something had happened, and we kind of chewed our fingernails trying to figure out what we could until it came back into view for at least one telescope. But when it came back into view, this is actually the AAVSO group of amateurs I got in touch with them back when we first found it, and they were keeping an eye on it for us. And sure enough, when it came back, it was a full magnitude brighter. When we managed to get an X-ray telescope pointed at it, it was brighter in X-rays too. So it had actually started accreting. It had gone from this one, the nice clean pulsar system where we can measure everything, to this one, which is the spectacular accretion where we're trying to understand the physics. So we've now turned on the accretion machine in our laboratory. We're trying to understand what's happening. And again, to get a handle on what's happening, we again need to use a whole range of instruments with a whole range of wavelengths, because each instrument and each wavelength probes a different part of the system. So the optical, again, tells you about the companion, which is actually being heated by more than it was before. It's considerably brighter. Also, the outer part of the accretion disk is relatively cool, meaning only as hot as a star. The outer part of the accretion disk you also see in the optical. But if you want to understand the inner parts of the accretion disk, they're so hot, you look at them with an X-ray telescope. And more, the infalling material, some of it falls on the neutron star surface, asterisk, some of it falls on the neutron star surface, and that we see in the X-rays also. So we need all of optical and X-rays to understand the accretion disk. What's more, like some of these quasars, this thing is spewing out a jet of material into the interstellar medium. And to see this jet, we know there's a jet here because we can see it with a radio imaging telescope, with a VLA. Finally, and you'll notice there's a big question mark here, something in the system is making a whole bunch of gamma rays, much more than it was before. We don't actually really know what, but it's definitely brighter than it was before. And that's one of the outstanding puzzles. We'd like to know, why is this making gamma rays? So it takes, again, this whole huge range of telescopes to get a handle on what's going on in the system. And it's combining all this information that lets us study the accretion. And we've had lots of surprises from the system. And I'll just talk a little bit about one. This is going to be a little more theoretical. I'll get back to observing and optical stuff in a bit. But I want to talk a little bit about an example of why this laboratory, what of the puzzles we're finding in this laboratory, why this laboratory is telling us that our understanding of accretion is limited. Excuse me. So, we know the spin period, we know the magnetic field, we know how bright it is, we know how much material roughly is pouring in onto the neutron star. And there's a theory that says what should happen. You know, it forms a disk, it swirls inward, and if you put lots and lots of material in a disk swirling inward, it swirls inward, and it hits the neutron star. It just pours in, and the neutron star all gets hot. You get this nice, bright, spectacular, unpulsed X-ray emission. But to do this, it takes a lot of material. You have to have a lot of stuff pouring in. And so it should be way brighter than it is. So we're pretty sure this is not happening. So okay, let's turn down the amount coming in a little bit. If you have less coming in, well, it pours inward, it pours inward, it pours inward. But now the magnetic field of the neutron star is important, because magnetic fields have pressure. Or if you've tried, if you take a strong magnet, you try moving another piece of metal near it, you'll feel forces. The magnetic field affects things moving near it. And we know how strong this magnetic field is. And so at some point, as the stuff goes inward, it starts interacting with the magnetic field. And the stuff is kind of in orbit around, and the magnetic field is turning. And if it starts interacting in close to the neutron star, then the orbiting stuff is going faster than the magnetic field. So the magnetic field grabs it, slows it down, and if you slow down something in orbit, it's going to fall. And it falls along the magnetic fields, it falls on the surface, you get hot spots. And the hot spots on the neutron star are really hot. So you see them in X-rays. So you should see X-ray pulsations. So this is what happens if you have quite a lot of material falling on a neutron star. If you turn it down more, though, then again, it hooks up with a magnetic field. But where it hooks up with the magnetic field is further out. So it's going slower, and the magnetic field is going faster. And now the magnetic field speeds it up. And if you speed up something in orbit, you push it out. So instead of the stuff falling downward, it should be pushed out of the system. And indeed, we see stuff being pushed out of the system. So, this is what's happening. And this lines up, theoretically, with how much material we see falling inward. So this is what was supposed to happen. If you turn down the amount more, then the pulsar can clear all the stuff out of the magnetic field and turn on as a pulsar. But the problem is, this is wrong. Because we see hot spots. We're not supposed to. There's not supposed to be enough material falling in. But we see these hot spots coming from the neutron star surface. The X-rays go up and down as the pulsar goes round. So there are clearly two hot spots where stuff is falling on the surface. But there just isn't enough stuff. The magnetic field, we know how strong the magnetic field is. We know how fast it's going. It's not supposed to be able to get in there. And yet it is. So our theory isn't working. We need a new theory. And we're working with this great theorist, Caroline D'Angelo. She's got this suggestion. There's a so-called trap disk model where instead of stuff flowing inward constantly, you get sort of a reservoir that builds up and holds itself in tight. So it only takes a little bit of extra material to flow inward. Maybe. We still don't understand what's going on in the system. The system, because we know how strong the magnetic field is, how fast it's going, how much material is going in, is a great laboratory. And the laboratory is telling us your theory is wrong. Time for a new theory. So it's a great accretion lab. But we only got one. Or we only had one. And when you've only got one, and it lights up once every decade or less, it's a very frustrating kind of lab to work with, because you think, oh, I have this great idea. I'll set up this experiment. We'll observe it in this way at this point, and then it turns off before your experiment happens, and you have to wait a decade for it to light up again. Or maybe you want to know how it lights up or how it turns off. Well, that only happens once a decade, and if you miss it because it's the wrong time of year, tough luck, wait another decade. So just one is very frustrating. So how are we going to find more of these guys? Well, fortunately, we already have two more. The first one, the second one, 1023 was the first one. Second one found is called M28I. So it's in globular cluster M28. And we knew there was a pulsar there called M28I, and we knew there was an accreting thing there. It had a complicated name, which IGR, anyway, I'll spare you the name. But it wasn't until we saw X-ray pulsations from the accreting guy that we were able to figure out, oh, these are the same object. Because I don't know how many of you have looked at M28I. M28, I think it's southern hemisphere, so maybe not so many. But it's a cluster full of stuff, so there's lots of stuff in there. So it wasn't clear that these were the same object. But they are. And so this is an object that goes back and forth between accreting and being a pulsar. Unfortunately, M28 is kind of far away, so it's hard to observe this guy. But it is going back and forth, and that's really exciting. There's a second one found, XSS J1023+0038. It actually is very similar to 1023. It's in the galactic field. It's about the same distance. For some reason, the spin period of the neutron star is within 1% of 1023. It's remarkably similar. And an amateur astronomer, it had been sort of flagged as maybe an interesting variable star. And an amateur astronomer, Berto Menard, South African, I think, because this is a southern source. Berto Menard noticed that this thing had dropped in brightness dramatically in 2013. A bunch of went from 16th magnitude down to 18th magnitude. And again, this one varies a bit, but such a big drop in brightness was not typical. And in fact, once we had found 1023, we knew what to look for. This seemed like a promising candidate, so we went and looked, and indeed, it's like 1023, it was accreting then for almost a decade, and then it stopped, and it's being a pulsar now. So this is an object that's also switched between the two states. So great, we have three objects, two of them are nearby and we can study them. In fact, right now there's one in each of the two states, which is great, because then you can study the two states. But we still need more, because switching a decade, even if we have three of them, that's still frustratingly long and unpredictable between switches. So we'd like to have a lot more. So how are we going to find more? Well, we've got a few plausible candidates. There are certain pulsars, the redbacks and black widows, that share certain key features with the pulsar side of the equation. They've got a couple of weird features as pulsars, and the redbacks and black widows are actually very similar. So those would be great. Those might be our interesting ones to look at. There's a certain class of very faint X-ray binaries that are, again, quite similar to the accreting side of the picture. In fact, there's one in particular, again, sorry for the name, 3FGL 1544.6 minus 1125, that looks almost identical to these accreting systems. But we haven't seen it transition. And we've only got three objects. We could be wrong. Maybe this one just looks like that. But we really need to catch them transitioning. So how are we going to do that? Well, there's a few ways that we can try and do that. The transition for 1023 and for XSS, we saw in the radio, pulsations turned off and on. In the optical, it got brighter. And in the gamma ray, it got brighter in gamma rays. So how do we catch them? Well, we can watch them with radio telescopes, especially the pulsars. Radio telescopes can observe year-round, which is a plus. But these guys are fairly faint. Some of them are kind of unpredictable. They have radio eclipses. They sometimes don't show up, so you don't necessarily notice right away if they disappear. And radio telescopes are big and expensive, and it's hard to get time on them. So it's a little frustrating to monitor these for maybe a decade each and find out. Gamma ray telescopes, well, the Fermi Gamma Ray Telescope scans the sky, so you can just watch whatever source you want. But many of these guys are not very bright gamma ray sources. So they're not great. We're going to try, but gamma rays are not the right way to catch it. 1023 is a fairly bright one, and we were getting 1 gamma ray photon a day. And then it brightened to 5 gamma rays of photons a day, which is a big difference, but you need a fair number of days before you notice that you're getting 5 instead of 1 a day. So gamma ray is a possibility, and we're going to try it, but it's tough. But optical telescopes, going from 17th to 16th magnitude, or 16th to 18th magnitude, that's something you can catch. That's something you can catch with even a fairly modest telescope. Because these guys are fairly modest in brightness, 17th magnitude. It's not a binocular object, but it's still, you don't need Keck to see it. They show a small modulation when they're normal. But the change between accreting and not accreting is fairly dramatic. And the transitions are fairly rare. So you really want to monitor lots of them. But the monitoring is accessible. So these are accessible to amateurs. In particular, we've already got J1023 and XSS J12270 are in the AAVSO's catalog of potentially interesting sources. There are light curves for both of them. This is the 1023 light curve. There is one for XSS. And I'm putting together a list of other candidates, other plausible sources. And it's going to take a bit of work to figure out which ones are optically interesting and also plausible candidates, but we're putting together this list. And I'll put it up on the AAVSO, but when the transition happens, if you catch a transition, it's really exciting. We triggered follow-up with X-ray telescopes, gamma-ray telescopes, radio telescopes, these big optical telescopes. Last fall, when 1023 was lit up, we simultaneously observed with XMM Newton, Swift, the VLT with X Shooter, the VLA, the Westerbork Synthesis Radio Telescope. I think there were a couple. I think there was a smaller ground-based optical telescope simultaneously, like really observing at the same time, because this is such a puzzling source. So if you catch a transition, it's really exciting. There's lots of stuff to be learned. So I think this is an interesting opportunity. I think these sources are interesting. Of course, I think they're interesting, but I think they are interesting to other people as well. And they are optically accessible. So if you're interested in observing these sources, I'll try and put them on the AAVSO, but I encourage you to contact me at last name at astron.nl, Archibald at astron.nl. And I hope you think they're interesting too. Thank you.
So the gamma rays are interesting. There's a quark nova project underway with the University of Calgary. Any indication that the accretion could lead to that quark deconfinement in the core of the neutron star and cause a gamma ray burst at that with that interaction?
It's a good question, but actually we're at the other end, right? That sort of thing is going to happen. You have lots of accretion, and you push these guys up to really high mass, so the neutron star collapses. So that's going to happen when you have a lot of accretion in really massive neutron stars. This is actually really, really wimpy accretion. Normal accretion for neutron stars is actually 10 or 100 times brighter than this. So this is actually really feeble accretion. So these guys are not great candidates for sort of causing collapses. They are interesting. LIGO is interested because if you have stuff piling in, you might get mountains on the neutron star. You know exactly how it's rotating, so you can look for gravitational waves from these mountains. So there are interesting ideas, but unfortunately, they're not going to be good quark nova candidates, I'm afraid.
Oh, hi. Is it true that the accretion disks that sometimes form around neutron stars form large objects? I heard, in fact, I read a report that a planet formed around a neutron star from the accretion disks.
Yeah, so there definitely are neutron stars with planets. The first exoplanets, as we heard yesterday, were found around a neutron star. But these accretion disks in particular are tiny, right? The whole system fits inside the sun. So the size of the accretion disk is really minuscule. And of course, you also have the companion going around that would disrupt any protoplanet. So I think if you wanted to do that, you'd want a much sort of wider system with a much bigger, more spacious accretion disk. Also, you want it not to be too busily cooked by the neutron star, so you need a little bit more room. Yeah, this is a relatively weak magnetic field for a neutron star, but that's not weak in absolute terms. This is a pretty spectacular magnetic field. So yeah, I wouldn't put your cell phone there.
I understand that getting your PhD is I'm over here and sort of in the middle
Oh,
here.
hi.
Is a sort of a multi-dimensional learning experience. When something came up, do you submit the request to a hotline, or do you have to start exercising your personal list of contacts at various facilities?
It's mostly personal contacts. For one thing, the survey group was a fairly large group of pulsar astronomers, and so we had people with connections all over the world. But also, all the big observatories have target of opportunity or director's discretionary time proposals. Normally, if you want to observe with XMM Newton, there's once a year when you put in a proposal, there's a big competition, and they decide who gets time. But of course, if your object went off yesterday and is going to fade out a week from now, you can't wait. So they've got a procedure where you can put in a short proposal that says, here's this awesome result that we can get if you just give us time tomorrow to look at this object. And they look at that and they think about it and they try and decide whether whether your science is good and whether they can fit you in the schedule, and if they can, you get the time. But of course, you have to be quite persuasive, and your object needs to be really interesting. Fortunately, these objects are really interesting, and they think so too. So, there is a procedure. You don't have to know somebody, but it sure helps if you know who to contact. And the other thing is, it'd take a second to bring it up, but you saw all the different telescopes I was using. I mean, there's a certain expertise with any given telescope. They each have their own quirks, and so somebody needs to know how to operate that particular telescope. And I have a rough idea, but when you need to get exactly right, you need somebody with expertise with a particular telescope. And so I've worked with a lot of different people, and I know if I need this optical spectroscopy to be done right, I can call René Breton, and he can sort out the spectra just right. I'll know roughly what needs to be done, but if I need it done right, I have to talk to René. If I need to look at the X-rays, I can talk to Slavko Bogdanov, because he's got a lot of expertise with this particular X-ray telescope. So having connections all over the world is really important.
Great talk, Anne, but a very quick one. This kind of transients, are you interested in ZTF at all and the results from that?
Yeah, so this is kind of the competition to amateur astronomers, is that there are a number of transient factories and sky-searching instruments coming online now. So the Palomar Transient Factory, the Pan-STARRS. I actually have another light curve, much like this one, from the Catalina Real-Time Transient Survey. And when LSST comes on, of course, actually, this guy is too bright for LSST, but there are starting to be automated transient pipelines. The thing is it still can't be totally automated, because these guys are not constant, right? They vary even in their normal state. And so if it just sends me an email every time they vary, that's totally useless, because I get an email every day. So I need somebody, whether it's me or somebody else, to look at the light curves coming out and notice when it's actually brightened substantially, when it's deviated from its normal pattern. So even I've actually in contact with the Palomar Transient Factory, or no, with Pan-STARRS people. And they too, I'm going to give them a list of plausible candidates in their Pan-STARRS field. And every time they look, I think they'll probably just send me the light curve measurement, and I'll put it on my light curve and see if it looks reasonable. So it's not completely automatable at this point, but these are coming online, and they are promising. But somebody needs to notice when things changes, and that still takes a human. And that still is something open to amateurs.
Thanks.
Anne, here. Hi, Anne. My name is Eric. Thank you for doing this. My universe is I know it a little bit better now because of you. I have two questions. There's a term called propeller mode in the accretion. Could you explain that? And the second question is, if I was there, would this thing be sucking all the hemoglobin out of my blood?
I think your hemoglobin is safe because it's a chemical compound, it's not magnetic. But the magnetic field is pretty hostile by itself. And of course, this thing is putting out 13 solar luminosities of antiparticles when it's being a pulsar. Oh, no, sorry, half of that's antiparticles, half that's electrons.
I meant the iron.
The iron, you'd be kind of okay. Some of them, the magnetars, the magnetic field is so strong that just the magnetic field would kill you. Your atoms would be distorted into needles. But this is a weak magnetic field, only 100 million times that of the Earth. So the magnetic field is not friendly. Don't bring your credit cards. But the magnetic field directly probably won't kill you. There's lots of other stuff to kill you, though. Propeller mode. Propeller mode, yes. So that's why I've gone back to this slide. So propeller mode is exactly this idea that stuff flows inward, it's stopped by the magnetic field, and where it's stopped, at the inner edge of the disk, it interacts with the magnetic field. And depending where it stops, and this is the propeller mode idea, if it stops here, and I've tried to indicate this with my little arrows, then the stuff at the inner edge is going at one speed, and the magnetic field is going faster. So when the magnetic field drags at the inner edge of the disk, it speeds stuff up. Speeding stuff up that's in orbit tends to make it go back out. So instead of letting stuff fall into a star, it propellers it outward. And of course, there's disk in the way, so it can't really go outward that way, so we think it goes up and down out of the disk. And so we thought, before we looked closer, that, oh, this is a propeller mode system. This is a nice, clear example of propeller mode accretion. Great, except not great, because stuff is falling on the surface too, and that wasn't supposed to happen. So the idea behind propeller mode accretion, you can eject stuff due to the magnetic field and the rotation, is certainly happening in the system. We see the stuff being ejected. But it's not as simple as propeller mode, because stuff is also falling on the surface. So we've had this discussion with some theorists who are really attached to propeller mode, and they say, oh, it's still propeller mode, you just have some stuff falling on the surface. And the accretion people say, oh, it's still accretion, you just have some stuff being ejected. And I think it's mostly terminology, but it's obviously something a little more complicated that's happening. But that's exactly it. We are testing this propeller mode idea. We have a system where we know the magnetic field, we know the rotation, we know enough about it to know that it should be in propeller mode. And we see that what's actually happening is a little more complicated.
Yes, thank you. Any observational evidence as to limit the duration of the transition from non-accreting to accreting or vice versa?
That's a very, very interesting question, because we think there's no accretion disk when it's being a pulsar, and there clearly is one now, and it's supposed to take a while for an accretion disk to form. So if we can tell how long it takes, that would tell us something great about accretion. Unfortunately, when this transitioned, it transitioned in sun constraint. It transitioned in June when you can't look at it with optical telescopes, which is how you see the disk, or X-ray telescopes, which is how you see the inner disk. So we're not totally sure, but we can narrow it down to about 3 weeks between when it, well, it's a little tricky. We see the, let's see if I can bring this up. There we go. We see the gamma ray brightening happens within about a few weeks. So whatever happened, it seems to have happened within a matter of a few weeks. And that's already uncomfortably close for an accretion disk to form from scratch. M28I, unfortunately, our best constraint is going the other way, the accretion disk disappearing. But M28I seems to have gone within a matter of days from full-fledged impressive accretion to nothing. So they do seem to transition quite quickly. But it's going to be really hard to tell for sure until we can catch a transition that's not in sun constraint, which is one reason I'm trying to push so hard for people to monitor these guys, so we can catch it as soon as possible after they transition. Because the time scale it takes tells us something deep about accretion physics, and I would love to know the answer.
An engineering question.
All right.
Regarding rise and fall times of the pulsars,
Yeah.
as an engineer, I've measured down to picoseconds and can get characteristics of semiconductors from that. Is your resolution that good to actually see characteristics of different stars?
That's a tough question. So when we measure pulse periods to stupendous numbers of decimal places, we can do that because we can count every single pulse. For this pulsar, I know exactly how many pulses there were between about 2008 and 2013. I know there were, 10 billion ... and 3, and not and 4, or not and 2. I know exactly how many pulses there are. So I can just take the time between the arrival of pulse number 0 and pulse number 10 billion ... and divide it by the number of pulses and get a really exact pulse period. So in that sense, we're not getting super precise time measurements. We're covering a huge span. So in that sense, we don't have to get really precise individual time measurements. Now, some of the nice, cleanest pulsars, we can get time of arrival measurements down to about 50 nanoseconds, which is pretty impressive. But again, there's a certain amount of averaging there. But closer to your question, if you look at the Crab pulsar, it sends radio pulses, but they're actually not exactly the same. On average, they're pretty steady, but each pulse is a little different. Once in a while, there's a giant pulse, which is a lot brighter than the others. And in fact, this isn't really true anymore, but if you have an old analog TV and you turn it on to an empty channel, and if you know when to look, you could see the flash of the Crab giant pulse lit up your screen. Now, of course, you have to know when to look, or else the flash could be just general snow. But they are really, really bright. And so people have tried to actually measure how long they are, because the giant pulse is actually really short, shorter than the normal pulse. And it's very tricky because you've got a limited bandwidth, as I'm sure you realize that if you've got a limited bandwidth, that sort of limits the time scale. And the interstellar medium gives you multipath propagation, which complicates things. But there is evidence of single pulses from the Crab pulsar, single giant pulses that are less than a nanosecond long. And this is bright enough to see on Earth. It's less than a nanosecond long, which kind of means it has to have come from a region no bigger than about this. Has to have produced this single spectacular flash of radio that we can detect. And it's acting coherently. It's a laser-like process. It's spectacular, and we do not understand how that happens. But that was done, in fact, that was actually done with a digital oscilloscope, because our normal instrumentation isn't able to do this. They took a really wideband receiver, and they hooked it up to a digital storage oscilloscope, and a normal pulsar back in. And when there was a bright pulse, they triggered the retain function on the oscilloscope. So then they had this really wide bandwidth, and they just kind of analyzed it almost by hand afterward to figure out that this was an incredibly, incredibly short pulse. So we can get these high time resolutions, but it's really hard. Yeah.
Hello.
Hi.
I was wondering if you said you know how the speed is slowing. Can you model back in time to determine the width of the accretion disk, say, 1 billion years ago, and look at its evolution?
Well, so if the pulsar was all by itself, we can sort of track back how quickly it should be spinning down and figure out how old it ought to be, because it was presumably spinning. The faster it goes, the faster it spins down. So you can trace that back to when it sort of must have started. But the problem is the accretion disk could be spinning it up. If stuff falls on the surface and swirls inward, it can make the pulsar go faster. Or if it's doing the propeller mode accretion, the pulsar is driving stuff out, so that could be slowing it down more. So unfortunately, tracing it back is very complicated because we don't know the history of accretion. And in fact, I mean, we know that it got from slow to fast by accretion. But if we want to ask what it's doing right now, in fact, I'm working with a grad student, Amrita Chowdand, in Amsterdam, we can actually measure how fast it's rotating now, how fast it's been spinning since it disappeared. Because we have these X-ray pulsations, we can measure its rotation since it started accreting and see, is the accretion making it go faster? Is the propeller making it go slower? And in fact, what we found is that actually it's spinning kind of just the same way as it was before. It's losing energy just as if it was a normal radio pulsar, just as if the accretion didn't matter. And that, again, was a total surprise to us. That was not supposed to happen. Pulsars produce these amazing radio things in a vacuum. If you fill the vacuum with falling material, shouldn't that stop the pulsar-y stuff? Apparently it didn't. So that's another surprise. We're currently putting together a paper to try and describe and maybe figure out. So it's absolutely, looking at the spin-down history of this pulsar is really interesting, and we're working on it.
We have one over here.
All right?
Hello, Ed.
Hi.
With the propeller accretion, just as an analogy, with an icebreaker and we break off a blade on the propeller, we get serious impacts of heavy ice into the stern. Is it possible that the actual material that created the neutron star has some, a point where there's no magnetic field or a less intense magnetic field that would allow the material to come in rather than be pushed out? Is there any way to assess whether there's a disproportionate material in the neutron star that changes the pattern of the magnetic field?
It's a good question. Now, this is a very, very old star, right? So it's had 1 billion years since it formed for things that kind of smooth out and end up with just a simple field. But of course, it's also accreting, and accretion is a very turbulent process. And we really don't understand. You start a simple dipole field, we understand, but it's not a dipole field, even if you don't have accreting material. And so the structure of the magnetic field is complicated. And in fact, some of these detailed magnetohydrodynamic models, some of the people who model the inflow of material, they actually seem to find that even if you're propellering vigorously, you can still sneak a bit of material. There's still some place in the magnetic field where you can sneak some inward and get onto the surface. So it looks like maybe it's actually possible to smuggle material inward, almost even if you've got most of it is being expelled.
So they would have a way to map that broken propeller blade to find out where it's sneaking in?
I mean, unfortunately, we've got sort of a very small amount of data as input and a very large number of unknowns. And so they can find one particular way it might work, and you can tweak some assumptions to find a different way it might work. It's very difficult, given how little we know about the systems, to nail down exactly what's happening. But yeah, they can try and map out magnetic field structures that can do this. And of course, the more observations we have, the more constraints we have, the fact that we know so much about the system narrows down the space they have to explore tremendously. And in fact, because we found this only in the last year or two, the modelers haven't caught up. They haven't started modeling this specific system. So now that they know more, they may do a much better job of mapping what's really happening, I hope. We really need them to sort out. We have a lot of observations. We need a lot better theory. So I'm trying to twist the arms of some theorists at the moment.
We have to cut off questions.
Well-
I'm in awe. Are you in awe?
Well, thank you all for all your interesting questions. That was fun.
Oh yeah, you got a vast knowledge inside that head. We have a few things to give you. One of them is the plasket medal. I'd love you to open that for us here so we can all
Thank you.
have a look at it. There's also a $750 honorarium and
My
a
goodness.
delightful medal. Ooh, look at this.
I should hold it against a black background.
That's the reverse side. On the obverse side is a picture of J.S. Plaskett.
Well, I like the side with the telescope.
And the Plaskett telescope is on the back. And your name. Right on.
Oh, yes.
And we have a certificate here from Casca and the RASC, signed by myself and Dr. Christine Wilson, for you to keep.
Thank you.
Thank you. We just loved your talk.
Yeah.